Hello again, Physics 1 students. Um, this is a video where I want to talk about the concept of equilibrium and stability. And this is an extension of what we've already seen. Now we want to incorporate the concept of torque. So the basic situation is going to be, well, before we said that equilibrium implied F net equals 0. Now we're going to enlarge this to say that full equilibrium means not only is the net force equal 0, but also the net torque is equal to 0. So if you see an object which is not moving, it's not rotating, well, then you know it's in equilibrium. In actuality, you could have something moving at a constant angular velocity or with a constant linear velocity. Those would still be in equilibrium, but to be quite honest, typically the situations we have in mind, nothing will be moving. So it'll be like a bridge or a crane or something like that. So that's the concept of equilibrium. Stability is is related to this. Stability has to do with, is something going to rotate? Yes or no? So basically it's a question, can you maintain equilibrium? So for example, imagine we had a skateboard. It'll be a really big skateboard, or we'll have a leprechaun on top. Okay, if the person is there in the middle, well, presumably it's stable. But if the person were to walk out towards the edge, there would be a point somewhere beyond which, if the person were to stand, the skateboard would start to tip. Okay. So if the person gets too far on the edge, the skateboard will tip. And right at the moment of impending tippage, I don't know what else to call it, the normal force on the other wheel would have been 0. So here's the basic idea for stability. Okay, when you have an object and it has some sort of a base, it could be a shape, it could be 2 wheels, whatever, some sort of a base. And assuming there are no outside forces acting on this, what you want is to make sure that the center of mass of this object is in between the base. Such that the center of mass is centered on top of the base. If that is true, then it won't rotate. If, on the other hand, the center of mass gets outside the base, then if you use the edge of the base as a kind of an axis of rotation, you'll see that there's a net torque and it would want to rotate. So that's generally how I approach a lot of stability problems when it's just gravitational weights acting. I just calculate the center of mass of the shape and make sure that it kind of lies within the base. Okay, so that's just a comment. The last thing I wanted to do in this video, or what I really wanted to do in this video, was to analyze a problem where there's a crane or a hanging sign. So here's the situation I have in mind. Let's imagine there's a wall, and there's a wall, and we're going to imagine that there is a pole and we're going to imagine finally that there's a sign or some sort of object hanging off the edge. We'll go and say this weighs 100 kilograms. And we're going to have a wire let's go ahead and have the wire attach, somewhere not all the way there. So let's give some units here. I'm going to say that this is 1 meter, this side. I'm going to say the total length of this pole is 2 meters. I'm going to say that this distance is 1.5 meters here. There's going to be a tension on this wire, and I'm going to say that the mass of the pole is 30 kilograms. So what I would like to know is, considering that we assume that this is not moving, it's stationary, so it's in equilibrium, what is the tension on the wire? Okay, that's what I would like to know. What is the tension on the wire? Sorry, I lost my screen. There we go. Now I'm back. All right. So I want to find the tension on the wire. To do this, we need a free body diagram. And let's make the free body diagram of the pole. And okay, so the first thing we have to do is let's kind of list all the forces at play acting on the pole. So I have the wall, pole, the wire, the hanging mass. So acting on the pole, the list of them, well, there's some sort of a force acting at where it touches the wall. And in reality, it could be some combination of friction and normal force. So there's some sort of a force here. I'll just make a guess that has some horizontal component and some vertical component. I don't know what it is. It's a mix. There's a tension. There's the downward force coming from, ultimately, it's really a tension, but it equals the weight of this sign. So I'm just going to go ahead and, I guess I'll say this tension here. So I'll call this tension 1 and tension 2. And then you also have the weight of the pole itself, which acts at the center of the pole. Well, the goal is to find the tension on the wire. We have knowledge about the mass of the pole, so we can figure out the weight of the pole. We can figure out the tension on this wire. The one that we don't know much about is actually the force at the contact point. So here's what we're going to do. There is no rotation. It's an equilibrium. Or, turn that around, you could actually consider any point to be the axis of rotation and just require that the torques add up to 0 about it. And in particular, since I don't know very much about this contact force at the wall, I ought to make this my axis of rotation, because then the unknown force will generate no moment about that point. So that's what we're going to do. We're going to mark the wall, and we're going to have, so here's the pole. We're going to have the weight acting down halfway. A little bit farther, we're going to have the tension. And then on the end, we're going to have tension 1. We're going to have tension 2. And we're going to require that all of these forces generate no net torque. Okay, so I need to work out, well, let's see, what's the torque due to the weight? You might say, well, wait a minute, didn't we say the torque due to the weight is always 0? No, the torque of the weight is only 0 about the center of mass of the rod. But we're not working there, we're working out here where the rod touches the wall. So actually, that's going to be the torque to the weight is going to be a negative torque. It's going to equal the mass of the rod times G times the moment arm, which is just the length of the rod divided by 2. And it's straight down, so the angle between them is 90 degrees. What about tension 2? I know that tension 2 just equals the mass of the sign times G, because it has to support the weight of the hanging mass, of the hanging sign. And I know that it's going to give rise to a negative torque about this pivot point, and the lever arm or moment arm it has is the full length of the rod. So the torque due to the sign is simply going to be minus the mass of the sign times G times L. All right. Finally, the torque due to tension 1. I don't know the tension 1. I know that it's going to generate a counterclockwise torque, though, so I know it's a positive torque. And I want the part of tension 1 which is perpendicular to the rod. So I'll need to find an angle here, theta. So I'll say it's T1 sine theta. That'll give me the perpendicular component times the lever arm. And going back here to look at my figure, that was this 1.5 meter number. Those are the three torques that are generated about the contact point with the wall. So let's plug in some numbers and see what we get. Requiring that they're in equilibrium says they should add up to 0. And from the weight, I said that the weight of the rod, or pole, sorry, was 30 kilograms. This was 100, 2 meters. Okay, while we're at it, just looking at things, let's find this angle, because we're going to need that. So I can get that by taking inverse tan of 1 divided by 1.5. And I find that this angle is simply 33.7 degrees. Okay. So I'm going to have minus the mass of the rod or pole, which I said was 30 kilograms, times the lever arm, which would be L over 2, which is just 1. This is for the weight of the pole. Now I get the weight of the hanging sign, which is going to be, oh, I forgot to multiply by G, 30 times G. Sorry. Then I should have 100 times G times the lever arm for the hanging mass. That's it's 2 meters. And then I get plus the unknown tension 1 times the sine of 33.7 degrees. That's the perpendicular part of the force, times the lever arm associated with the tension. That's a 1.5 meter amount. And I can turn all this around and solve for T1. So this gives me okay, assuming I've typed all that in, I find a result of the tension force equaling 588.8 newtons. Now that we know that, we can actually work backwards and find and figure out the contact force. So what about the contact force? Well, let's think about that. When I look at the forces acting on the pole, there's the tension, the weight, the other tension, which, so I now know all those numbers. And this unknown force must have some x and some y component. I don't know what they are. So I'm just going to call them force in the x direction and force in the y direction. So when I add up the x components, F net in the x direction, well, there's going to be something from the wall, which I don't know, and the weight x down, the hanging mass x down, and then I get the wire pulling to the left. So it's going to be minus T1 cosine of theta. And that has to equal 0 because it's an equilibrium. Similarly, the net force in the y direction, well, I don't know whether it's positive or negative, so I'll just write Fy and let math tell me whether it's positive or negative. And then I get a positive contribution from the upward pulling cable. And then I get downward contributions from the weight of the pole and the weight of the sign. And again, this must equal 0. So we can just do algebra and solve, because I know tension 1, I know all these other numbers. We can just solve for this. So working this out, this tells me that the force in the x direction covering the wall must be 489.8 newtons. And this tells me that the force in the y direction coming from the walls must equal 30 times 9.81 plus 100.81 minus make sure I'm doing that right. Okay, when I do the algebra, what I find is a positive 948.6 newtons. So it turns out the way I drew it was correct. I guess you can kind of see that because you probably need, well, I don't know how obvious that is, but anyway, it turns out it's that way. It could have been that in fact you needed a downward force depending on how things were kind of hanging and the positions of things and the sizes of the masses and things like that. So that's how we can solve for the force at the wall. And that's pretty typical. Usually when you have some sort of a hinge mechanism, something like that, a lot of times you first figure out what happens away from the hinge. And once you know everything else, you can work backwards by requiring that all the forces add up to 0 to maintain equilibrium, and you deduce whatever must be coming from the hinge. Okay, so hopefully that was a good example for you.